All right. So let's look at another example to understand linear transformations better. Okay, because they tend to be confusing. I have studied, I would say, quite a lot of them since the past few days, and I still get confused at times. So I'm just making this video to understand it better and maybe to make it simpler for you. Okay. So, of course, these videos help things make simpler for myself, but if it can help you as well, good. So, anyway, let's cut to the question. See, okay, let me write this linear transformation. Okay, G is the linear transformation. It is a linear operator. What does that mean? That means it is a transformation from Rn to Rn, n-dimensional space to n-dimensional space. Such a linear transformation is called a linear operator. That's it. I hope you already know this. Okay. So this is the linear transformation, and it is defined as 2x minus 7y and 4x plus 3y. Okay. Yeah. So what this means is that, like, this is specifically from R2 to R2, right? Like G is from R2 to R2. Now, this means that, okay, let me tell you first what it means. Or I'm not sure if I've already discussed this. Anyway, let's do it again. It means that any vector, okay, I don't like this thing relating it with, like, looking at linear transformations from a geometrical point of view. It is good as long as we are in two-dimensional space or in three-dimensional space. But beyond that, it is just mind-boggling. I mean, sometimes I wish I had not seen those videos, but still, they help a lot in understanding. So I would suggest you to check out Three Blue and One Brown. Wow. Three Blue, One Brown or Khan Academy. Okay. Check out their videos on linear transformations, like geometrical representation. Check them out, understand them, and then try to forget them. Okay. So what linear transformations do is that, yeah, it's too simple. Okay, we don't need this. We don't need this. Okay. So what it is doing is that I have a vector in x comma y, and it transforms it into this thing. Okay. So as an initial step, let's do this. Let's take the general basis represented as E1, which is 1 comma 0, and E2, which is 0 comma 1. These are the general basis for a two-dimensional field. Sorry, oh my bad. Two-dimensional vector space. Okay. So let's find what is G of 1, 0. Simply plug in these values. X is 1, Y is 0. So we get 2, and again in this x is 1, y is 0, 2 comma 4. Okay. So what? So this means that the point 1, 0 is being mapped to this new point. Okay, let's put in a little geometry. Point 1, 0 is this. So this is being mapped to 2 comma 4. Okay. So this basically means this vector has been transformed to this vector. Okay. Okay. Now, similarly, you can find g of 0, 1, which will be negative 7 and 3, right? So this means that, what does this mean? Yeah, look, this means that 2, 4, negative 7, 3. If we put this in a matrix and we multiply it with 1, 0, even, which we took, what will it give us? 2 times 1 minus 7 times 0. It gives us 2, then 4 times 1, and 3 times 0, 4. This is what is actually happening. So it is mapping this matrix is mapping all the points to these points. So if we plug in, it got a little messier, okay? Anyway, sorry. If we plug in this and negative 7, 3, and x and y here, if we just do this matrix multiplication, we will get 2x minus 7y and 4x plus 3y. This is how we are getting to this, okay? It is good to know both of these forms for a better understanding. Sorry for the noise. Okay, so now let's address the change of basis. Okay, this is our standard basis, and these transformations are actually with respect to these bases. What that means is that take any a and b in our domain, this one, take any ab, so they are written as linear factors of our standard basis. They are written as linear factors of these bases, okay? But we know that any two linearly independent vectors in R2 can act as a basis, and any other vector can be written as a linear combination of them, right? So with that in mind, let us define a new set of bases, say S, and S is the new basis, okay? And it is defined as U1, U2, which is actually, by the way, which is, let me write this, and 2 comma 5. By the way, I'm referring to Shom series, linear algebra. These examples are taken from them, and it is a pretty good book to practice. Like, I like it when I have solutions to verify whether I'm going in the right direction or wrong direction. So it is a good book. Okay, so you can find these examples there and more to practice. Coming back to this, so this is a new basis. Now they're asking us, okay, one thing I skipped. It is yeah, say I call this P X or Y P. Let me call this G X, and let me call this as A. Okay, so Gx gives us A, and if you need to find the inverse transformation, you can find the inverse of this matrix. Wait, let me, like, if you multiply G inverse on the left side, then this will become identity, and what we are left with is X equals G inverse A. So the inverse of this matrix, the inverse of these matrix, let us find out. Okay, it will be a good exercise. 4 3. Since it is a 2 cross 2 matrix, it is easy to find the inverse. What is the determinant? The determinant of G is 3 2s are 6 and plus 7 4s are 28. 8 and 6 14 34. Yeah, 34 is the determinant. Okay. Yeah, why not? And now the adjoint. So in place of 2, I hope you already know this. Then negative 7, negative 4, and then transpose negative 4. This will be 7 and this will be 2. And we divide this by 34. So this is supposed to be G inverse. Interesting thing we've got. Okay, let's look at this. What was happening here? 1 0, this 1 0. When we were operating this matrix on our base vector, we were getting 2 4. Okay, now let's apply the inverse to 2 4. Let us take this on the left and operate it with 2 4. Let's see what we get. Okay, so 3 over 17 plus 20. Oh, why? 14 over 17. Yeah, nice. Then negative 4 over 17 plus 4 over 17. Bingo. See? This is 14 plus 3, 17 over 17, which is 1, and this is 0. So we are again mapped back to the vector which was given to us when we applied this transformation. Okay, I was not intending to do this in this video, but since we have done this, and if you're confused, watch it again. It is pretty simple. Do it yourself, watch it again. I'm pretty sure you will understand it. Okay, yeah, so yeah, this is one thing that I wanted you to know. Now let's move back to this. So what is happening here is that now we have these new bases. Okay, so earlier our bases were E1 and E2, the standard bases 1 0 0 1. Okay, and our transformation matrix, which was, I'll write it here. Our transformation matrix was, I think, 2 4 negative 7 3. Yeah, this was our transformation matrix. Now they can ask us to find a transformation matrix. Okay, there is some notation, GS, something like that. It is very confusing to me, so I'll skip that. Okay, I don't know why it's confusing to me. Anyway, moving ahead. That is why I'm making this video, so that you can get over those notations and understand the concept. So what is happening here is that this is the transformation defined according to these bases. That means that when each vector is represented in the linear combination of these two vectors, then this transformation works for us. Now they are saying that we need to define each vector in terms of these base vectors. Then what would be the transformation? Because we should still be able to map a given vector to the same vector, no matter if we use this basis or this basis. Any chosen vector in our domain, no matter which base vector we use to define that vector, should go to the same vector. If x goes to y after applying a, then x dash, oh no, then, and if I have defined these as linear combinations of e1 and e2, then if I define x and y, they will still be the same vector. But if I define them using u1 and u2, these new bases, then which transformation matrix would work? That is what they want to know. Okay, so let's find it out. So how we do it is, yeah, we have our transformation with us, and what we do is that we first evaluate that where this u1 and u2, to which vector are they being mapped according to our transformation. So I'll write the transformation again. G of xy was 2x minus 7y and 4x plus 3y. Just plug in x and y here and we will get the transformation. Okay, now I want to see this new basis they are asking us, where are they being mapped to? Okay, let's find it out. 2 7 3s are 21 and 4 plus 9, which is negative 19. 9 and 4 13, right? I tend to make mistakes sometimes while calculating, so if you think I made a mistake, just read the description of the video and you will hopefully find the correction there, because I've still not figured out how to add a message between the video. Negative 31 and 8 and 5 13, so 23. Anyway, sorry for this blabbering. Okay, so yeah, now this is what happened. The linear transformation is mapping 1 comma 3 to this and 2 comma 5 to this. Now what are they asking us? They are asking us a transformation when the base vectors are these. Well, if these are the base vectors, then let's define these in terms of the given base vectors, because so far they were being defined using these standard bases. So now my job is to find this in the terms of alpha 1 as a linear combination of my new basis, which is this u1 and u2. Okay, pretty standard. I hope you already know this, like what we are just doing. Okay, so this gives us alpha 1 plus, now this is, I'm multiplying this and adding x coordinates, then I'm adding, and then I'm multiplying this and adding y coordinates. Alpha 1 plus twice of beta 1 comma 3 times alpha 1 plus 5 times beta 1, right? Looks funny, but I hope, yeah, you are smart enough. Okay, so this is what is happening. Now we have got two equations. I'll write the second equation first, which is 3 alpha 1 plus 5 beta 1 equals 13. And our second equation is actually alpha 1 plus 2 times beta 1 is equal to negative 19. Let's eliminate alpha, multiply this by 3. So I get 3 alpha 1 plus 6 beta 1 equals 2360. So 19357, negative 57. Okay. And now subtract this. This cancels out. I'm left with negative beta 1 equals, is it right? I hope. Yeah, it is 70. So my beta 1 is 70, and alpha 1 I can calculate from here, negative 19 minus twice beta 1, which is 70. So this is negative 19 minus 140, 150, negative 140, 50, yeah, 159. Okay. So this is, oh my god, see, I made a mistake. Yeah, and this is what I was saying. If you see me making a mistake, this will be negative. If you catch a mistake which I'm not correcting, then just go to the description. So 140 minus 20 is 120, and minus 19 will be 121. So this is it. Alpha 1, beta 1. What I just calculated is that negative 19, comma 13, when written using the new basis, is 121 times u1 plus, sorry, minus 70 times u2. u1 and u2 being these new bases. Okay. Yeah. Now the second vector, 2 comma 5. You remember how we got this? We found out where this transformation was sending the first base vector. Now this transformation is sending the second base vector to this vector. So let's write this vector as a linear combination of the new bases. And I will do it in a slightly different way. They both mean the same thing though. This, I should be able to write it as alpha 2 times the first base vector u1 and beta 2 times the second base vector. Right. This thing and this thing, they're pretty much two different ways of doing the same thing. Pick whichever way you like. Okay. So let's do this. I think this is neat, and I think this is like simple, easy to understand. So yeah, let's do this. This is alpha 2 plus 2 times beta 2. This will multiply with everything. I'm skipping steps. It is very simple. I hope you already know this. But still. Okay. And next step, I add those vectors. 3 alpha 2 plus 5 beta 2. Right? So again, I have with me two equations. The first one I'll write here, alpha 2 plus 2 times beta 2 is negative 31. And the second one is 3 alpha 2 plus 5 beta 2 is 23. Okay, so let's eliminate alpha 2. So I will multiply this by 3. So I get 3 times alpha 2 plus 6 times beta 2 is equal to 33s are 90, negative 93, and subtract this. So this cancels out. I'm left with negative beta 2 and 3 and 3, 6, 9, 10, 11, 116. So my beta 2 is negative 116. And my alpha 2, I'll just plug in beta 2 here. So alpha 2 is negative 31 minus 2 times beta 2, which is negative 116. Okay, big numbers. 31, this is positive. 110, 220, 230, 232. Okay, minus 31 is 201, negative 201. Positive 201. Okay, right. So what now? Now I evaluated these alpha 2 and beta 2. So let us combine this. Let's combine this. Okay. Let's save some time. Damn it. Yeah. So where was that 2? It was here. Yeah. So in place of alpha 2, now we have 201. Let me write these values. In place of alpha 2, I have 201. And in place of beta 2, I have negative 116. Right? So, and about the first vector, this is what I have for the first vector. Right? So, what now? What does this mean? Well, this means that the transformation matrix, see, 201, okay, wait, no, 121. Let me just write it first and then I'll explain. Okay, this will be the transformation matrix according to these bases u1 and u2. Okay, and why so? Well, because if you apply, see, when you apply 1 3 here, what will you get? Check it out. You will get the same, these. Okay, let's check it out. So 121 minus 603. Okay, that's nowhere clear, nowhere near that. Okay, sorry for that disturbance. Wait, what is this? Backspace. Okay. Yeah, see, I told you, they're still they're confusing, but I need to explain how this matrix works. What did we find out? Oh yeah, see, now we calculated these vectors, and this is the coordinate matrix, or is it called that? Okay, I'll cut short this video, or no, let's just be. This is the new matrix, transformation matrix, and let me write the first matrix, which was 2, 4, negative 7, 3. Okay. Now check the trace is 5. The trace of this is 5. The determinant of this was 34, and you evaluate this, the determinant of this will also be 34. Okay. And why is that? Because these two matrices are representing the same linear transformation. They are mapping each and every vector to the same vector. It is just that in this case, the vectors are defined with this basis. And in this transformation, all the vectors are defined with each new basis. Okay. So that is it. And it will take me a lot of time to figure out now. So just think over it, do some brainstorming, do a lot of questions, and you will figure out why this is the new transformation matrix. Yeah, I think that is it.